In the previous lecture, we learned about the total energy of a in total energy in SHM, which is given by kinetic energy plus potential energy. And we see that the total energy is a constant. This is also the maximum value of potential or kinetic energy. Thus, at the time when the potential energy at its maximum value, the kinetic energy is 0 and vice versa. Means when potential energy is maximum, kinetic energy is 0, and when kinetic energy is maximum, potential energy is 0. Next, we know that we have k equals to omega square m, and we have omega equals to 2 pi by t, or 2 pi n, where n is the frequency. Again, we write E equals to total energy 1 by 2 k a square equals to 1 by 2 using this value omega square m a square, and again putting the value of omega 2 pi n, or this value 1 by 2 यानी 4 pi square by t square m into a square, or again if put this value, then 1 by 2 4 pi square n m into a square, or we can write this as 2 pi square m this will be n square, 2 pi square m n square a square. So this is the formula for kinetic energy, can be represented with this value also. Here we see that the total kinetic energy in SHM is given by 2 into pi square m n square a square. Here m is the mass of the particle, oscillating particle, n is the frequency, and a is the amplitude of oscillation. Thus, we see that the total energy of the particle is directly proportional to the square of the amplitude, a square, and inversely proportional to the square of the time period, and directly proportional to the square of frequency. Hence, if the potential energy in the equilibrium position is not 0, then this value must be added to our value of the total energy. Again, the kinetic energy is given by k equals to 1 by 2 k a square cos square omega t plus phi, and it is also written as 1 by 2 k into a square minus x square. That is, it means that kinetic energy also depends on the square of displacement x. So it acquires the same value twice in each oscillation. So we can say that its frequency is 2n. Next, so it is clear from this that the frequency is 2n. Now we will see the average kinetic energy and average potential energy in simple harmonic motion for a given time period. So let's see. So here we see the average kinetic energy. Is to calculate the average kinetic energy, we know that the displacement of oscillation x equals to given by a sine omega t plus phi and omega square equals to k by m, we know that, and the instantaneous kinetic energy is k equals to 1 by 2 m dx by dt to the whole square. This is v, so 1 by 2 m v square. Now using the value of x, we get 1 by 2 m omega square a square and cos square omega t plus phi, using x here and differentiating and then squaring, we will get this. So now we can calculate the average kinetic energy by integrating it in the over a one time period, that is t. So the time average of the kinetic energy over a period t of the motion will be given as k average equals to integration 0 to t. We are taking average in one time period oscillation. So k dt integration 0 to t dt. Now putting this value, so here 1 by 2 is constant, m is constant, omega square is constant, a square is constant. Only we have to use this in integration. So 1 by 2 m omega square a square integration 0 to t cos square omega t plus phi divided by, now take directly, this will be t, or you can write it as a t. We know that t equals to 2 pi by omega. Now using the trigonometric formula we can solve it. So here will be 1 by 2 m omega square a square, and using the value of t is equal to the we know that the t is also represented by 2 pi by omega. So using 2 pi by omega and integrating it, so first simplified it, so we can write it as a cos square theta is formula. We have formula cos square theta equals to 1 plus cos 2 theta by 2, so we can use that formula, or 1 plus cos 2 theta, here theta is this value, so omega t plus phi divided by 2, and here dt, it is integrated over t. Now solve this. This will be this will be, and this 2 and 2, this will be 8, 1 by 8 m omega q a square, and also pi, this pi will be below, and now integrating it, so taking separate integration, so first will be integration 0 to t dt plus integration 0 to t cos 2 omega t plus phi over the time period t. So we have 1 by 8 pi m omega q a square, and now put the value. Now because we know that t equal to 2 pi omega, so we can write this value as 0 to 2 pi by omega dt, and a plus integration 0 to 2 pi by omega and cos 2 omega t plus phi. So integration of this value will be 0, because in cos function in a one time period gives 0, and if we take the integrating and using this value, we will get 0. So 1 by 8 pi m omega square omega q, not square, omega q, and this will be 2 pi by omega plus this value is 0, so 0, and so we can write next to 1 by 8 pi m omega q a square into 2 pi by omega equals to pi cutting 2 pi with 8 pi and omega with this, we get 1 by 4 m omega square a square. So this is the average kinetic energy in one oscillation. By 4. Now again use we have we know that omega square equals to k by m, so use this value 1 by 4 m into k by m into a square, and this will be 1 by 4 ka square. Now we have calculated the average kinetic energy of the simple harmonic motion in one time period oscillation. Now similarly we can calculate the potential energy in one time period oscillation. And so let's first write the formula for potential energy, which is U equals to 1 by 2 kx square, and put the value of x, so 1 by 2 k, and x is a square sine square omega t plus phi. Next we have to take average over time period t. So the time average of the potential energy over a time period t of the motion is U average equals to integration 0 to t 1 by 2 k a square sine square omega t plus phi dt divided by integration 0 to t dt. Now we have to solve this. So next we can write we put the value and calculate it. So we can write this as again U average equals to 1 by 2 k square integration 0 to t. We use 2 pi by omega in place of t, 2 pi by omega, and sine square omega t plus phi, and this value will be 2 pi by omega. Or this will be equal to the 1 by 4 pi omega k a square into, now take the integration of this. First we change into the formula using trigonometric formula. This will be equal to 0 to 2 pi by omega 1 minus sine omega t. Sine square theta is equal to the 1 minus sine 2 theta. So using this formula 1 minus cos 2 theta, sorry, 1 minus cos theta. Sine square theta is equal to the 1 minus cos 2 theta by 2. So using that formula 1 minus cos 2 theta omega t plus phi in place of theta divided by 2. Now this is constant, so it can be out of the integration, and this will be 1 by 8 pi omega k a square into, take integration separately, 0 to 2 dt 0 to 2 pi by omega dt minus integration 0 to 2 pi by omega cos 2 omega t plus phi. Now 1 by 8 pi omega k a square into this will be 2 pi by omega minus again integration over 2 pi by omega, this value will be 0, and so we have 1 by 8 pi into omega k a square into 2 pi by omega. So omega and 2 pi 4 pi, so it will be 1 by 4 k a square. So again we see that the value of potential energy, average potential energy, is 1 by 4 k square. That is, we can write U average equals to K average equals to 1 by 4 k square. Thus from this it is clear that the time average kinetic energy is equal to the time average potential energy. Here we have written, because we have got time average of potential energy 1 by 4 k square and time average of kinetic energy as 1 by 4 k square. And so this is a characteristic property of the harmonic oscillator and is not true for anharmonic oscillation. So it is only true for harmonic oscillation, it is not true for anharmonic oscillations.